vector schmector. I've been talking a lot about vectors and how to normalize them and what to do with them, and right now we need to determine how we can use them to transform and orient objects in space. So before we do anything, go ahead and drop a cube on your stage, and I want you to just select it. And with it selected, go to the display, transform display, local rotation axes. And I'm going to go to wireframe, and I'm just going to move it off here in space. Go to wireframe. So in there you can see that there is a local rotation axis that's at the pivot point, and wherever I rotate this cube, there is a corner of vectors that rotate with it, and I call it a corner because it actually looks like the corner of the cube that I'm rotating right now, and they're all 90 degrees apart. Every object in 3D space, its rotation can be expressed as a series of vectors that are all at right angles from each other. So we can use those to calculate what's called Euler rotations, but right now we don't care about that. We just want to know the vectors. And I made a little visual here for you to see, so I can go back to shaded mode, and you can see this matches the local rotation axis. And I also added little annotations here that update live. So when I rotate and translate, these values will update, right? Okay, so to help us illustrate this a little easier. So this is great. Now we have an indicator of normalized vectors that are pointing off in the x direction, the y direction, and the z direction, and the translate. So we have values, 4 values here right now. So that brings us to what often people get dread horribly is the matrix itself. Well, PyMEL makes this a lot easier for everybody to work with. So this is your standard matrix, and this 4th column is responsible for shear and other things. We can ignore that pretty much for what we're going to do. So in PyMEL we can just not worry about this. So we're just going to be dealing with a matrix that is just 4 values that are 3 by 3, and we're going to go ahead and build that matrix. What we have to do is just plug in the values that we see floating on the x, the y, the z, and the translate, and we will create a matrix, and then we will use this matrix to force some other object to obtain the exact same position and orientation as the cube. Let's go ahead and do that. Okay, so first let's create an object. I'm going to create a polygon cone. I'll just pull it out. Whoops, just pull this guy out here in space and rotate him. Just put him wherever, it doesn't matter. Let's just call him the cone. I'm just going to say the cone. Okay, and I'm going to open up my script editor. Okay, and I'm going to clear my history here. I'm going to import PyMEL.core as PM as always. Let's say the cone. I'm going to make a PyNode real quick. pm.pynode, and I'm just going to say the cone. We've done this before in the PyNodes module, so you should be familiar with this. Alright, so now let's just create some vectors that we can plop into a matrix that we're going to build. And I'm going to move this up here a little bit. I've done this video several times now, and I keep moving my script editor accidentally off screen, so I'm not going to do that this time. This is going to be the last time. I promise I won't do this. So what we're going to do is we're going to take these values. So I'm just going to get over here and focus on this guy right now. So I'm going to say xvec is equal to pm, and don't worry, I'm not going to type all these, dot vector. Okay, and I'm going to go ahead and copy that. Control V, Control V, Control V. And I'm just going to change this to Y, Z, and then we'll just call this trans. Okay? And then let's just fill in the values. So for these little annotators, I actually made a script that lets me select them. And then if I went to the attribute editor, just down here, you can see the values actually here. So I can just copy that, Control Copy, Control V, and just plop in these values for where they are right now. So for the Y, I'll just select that, Control Copy, Control V, close parentheses. Do the same thing for the Z, which is right here. Let's grab that guy, Control Copy, Control V, and then for the translate, which is right here, I'm just going to grab him. The precision I've just limited to 3, but it could be much greater. I just don't want to have giant numbers rolling off the screen here that drive you crazy. So let's go ahead and make all those vectors. So if we look at each one, they are in fact vectors. And now let's go ahead and just build a matrix. So we'll say cone M, capital M, usually is what's used to determine a matrix. So when you're looking at somebody else's code, if you see capital M, they've built a matrix usually. So cone M, we'll just say pm.dt.matrix, and not matrix N. That's for odd-shaped matrices, not 4x4 matrices. And then all we have to do is put these in order: x vec, y vec, z vec, and trans. Let's go ahead and build that matrix. So if we look at this matrix, let's go ahead and clear our history real quick, and I'm just going to evaluate cone M. You'll see that I only pumped in 3 values, 0.33, minus 0.211, and minus 0.819, but it added the 4th value for me, so it added the 4 in there that I needed. So I didn't have to worry about this extra 4th column right here. It was just imported for me. That's great. And on the last one, instead of a 0, it puts a 1, which is what you want for the translate by default, if you're not shearing everything. It's another topic entirely. So I do have a matrix now. Now all we have to do is tell this cone right here. I'm going to close this so we can make it smaller and not go off the screen. I'm going to make this cone obtain the same position here. I'm going to go to wireframe mode so you can actually see it happen when it happens. So I'm going to tell cone M to do that. So cone M dot set matrix. I'm going to set you, and I'm going to set it to cone M. It's very simple. Oh, wait, cone M. I'm going to set that to, oh, the cone. I am totally tired right now. That is the object, and I'm going to send it to the matrix. So you saw that it just went there, right? This guy is just visualization right here. So it's scaled at 10 right here. So if I scaled him back down to 1, you would see that they did match up right here by the default. Their default builds. Another cool thing is you can actually just create a PyNode out of some object and then tell that other object to obtain that matrix. So it obtains the translate, rotate, whatever, without ever having to do like a point nor a constraint or anything. So let's do that. So we'll say we'll make a PyNode out of the cube. So we'll say cube, I'm just going to call it cub, is equal to pm.pynode. It's all cube. So we just made that PyNode there. And so instead of telling the cone to go to the matrix here, let's copy that. We're just going to get the matrix of some other object. So we PyNoded cub, and we could say cub.get matrix. I just want to make sure that that's a value first before anything goes awry. So yes, it does get a matrix. So all we have to do is get and set at the same time. Let's just test this. So let's move this out of the way real quick here, and let's scale everybody back up. So I'm going to say cube, you go back to 10, because if the cube is at 10, it should also scale the cone. Let's go ahead and see if it does that. Boom, it does. So let's rotate the cube in some arbitrary position, run that line of code again, and that's how you get positions. You get the matrix of one object, the cube, and you use it to set the other guy. It'll also get scale, so you have to be careful when you do that. Alright, so the question is, this is great, but how do we get these corners? These corners aren't given to us for free. We've got vectors. Let me pause this and open up the video of the other Maya file real quick. So I just opened up this file. How do we use this? And I've shown this to you briefly. There's a triangle. Here are some joints. Let's go ahead and turn off the joints, or we can just leave them on for this right now. There's vectors from these points to point A to point B. Well, the answer to your question, or the answer to my rhetorical question, is through the thing called cross product. And we're going to go ahead and talk about what it is and how to get it next. And once we get cross product, we can build our own corners, a set of vectors that are aligned in a corner. And once we have our own corner, we can, as you can see, we can assign that to any object's position and rotation in space. And that is how we're going to use matrix math and vectors and matrices and linear algebra to align our joints. And we're going to show you that real quick here. Then we're going to write a script to do it for any 3 joints.